Yeah, we do. You and Hannah, I guess. And Kyle, but that's not one of the
You guys just pass these along as you go down, one of each. Okay, I do want to make a couple of points. I guess I'm done. Okay, so a lot going on here. Okay, for those that are completely lost about the Daniel cell or battery in general, you shouldn't be. You should be picking something up at some point here. Okay, a lot going on. Absolutely, I'm going to give you even more. Okay. At some point I'll peel back and say this is what I'm going to need for the test, but this is what you need to truly understand it. You won't truly understand everything until the spring because there's thermodynamics in here that I have to go into detail. I'm giving you a prelude to that, all right, but we can't get totally there. But you can get a long way there, okay? And we're going to bring this back in the spring and be like, wow, I can't believe in September this is a problem. I love electrochemistry. But right now it's like, what the freak am I doing? Okay, I get it, and we're going to chip away at it, okay? So just trust me here, trust me, okay? Tonight's homework is basically the basic skills you need. This is a little more to show you what a AP question is. Now you've only been in AP chemistry for 2 days, okay? So if you looked at this part 2 question and said, oh my gosh, okay, give yourself a break. Now, I bet either through the video or just trying it and sitting down, you got a lot through it than you probably expect. And if you didn't, that's okay. Okay? Now, one thing I want to say is from Jump Street, you're going to see something different, okay, than sometimes written. All right? For instance, if I get nice up close and personal here, I guess I can get that personal. If you look at the overall reaction they gave you, they're giving you something called a net ion reaction. Okay? Now, I'm going to talk about this even more today and go a little farther, and hopefully through the discussion today, tonight's homework will make a little, I'm sorry, last night's homework, if you had a little trouble here and there, will be, oh, okay. I can't just say today is about vowels and tomorrow is about consonants. Things just bleed into each other, so I have to keep working and chipping away. And just their uncomfortable part is going to get comfortable if you just do what I ask. Now, this is called a net ion reaction. Okay? Notice they're just showing the ions. Okay? Now, in these beakers, I also have free ions. For instance, if I haven't told you already, in this beaker is zinc nitrate. Okay? Zinc nitrate. So zinc nitrate, if you remember from your naming skills, zinc we know can only become +2. You can learn that. Nitrates are NO3 -1. And I gave you a reference table to remember those things. Now, in college they'd ask you to memorize these, but you don't have to. So I gave you this yesterday, okay? And this is going to show you that there are some grouping of nonmetals or atoms that have charges, and they have particular names. So in this beaker, there's zinc nitrate. And I write it like this. There's one zinc, which we know when it reacts becomes something other than 0. It happens to be +2. It only can become +2. In the reagents reference table, you can look up and see what charges they like to become. Okay, this likes to become +2. Nitrate likes to become -1. These are all things you're able to look up in reagents, and you'll be able to do that in this course as well. I'm not having you memorize. So you're going to get at some point a reagents, okay, and let's just, for all intents and purposes, let's go there for a second. This is part of the reagents reference tables. And for those that don't know what I'm talking about, if I go to the periodic table, and here we go, and let's look at a good old-fashioned zinc here, okay, as opposed to upper right-hand corner, it's going to tell you it likes to become zinc +2. I'm going to explain when we get to some more details why it becomes +2. And until that time, you can just look these up. Okay? We're going to do this backwards and forwards so much, you'll know zinc becomes +2. I'm not having memorized that. We're going to understand why. And later in the course, you'll know zinc becomes +2, obviously, whatever, and you can be like snobs about it to each other. Okay, how do you not know that? I'm like, copper becomes +1 and +2. Ew, you don't know that? Can't sit here. Okay, so the point is, there's reasons for that we're not ready to discuss. You can always look this up. So for a test or a quiz that makes you write something, I give you that information. You have that, no worries. Okay, now, this is copper nitrate. You should know, or at least we're going to learn that copper or transitional metals give off colored solutions. We'll get to those details. This is copper nitrate, okay? And I put 2 outside the parentheses to say I need 2 of those ions. Easy stuff. Now, what is implied is that in a solution, we would write, if this is in solution, aqueous. Okay, we'd write that. And the reason why we write aqueous is to mean, for those, remember this summer, that's a homogeneous mixture. That is a solution. That means the first drop is the same as the last because it dissolves. Water interacts with these ions. So if I had solid zinc nitrate and I add water to it, it will dissolve to make a solution, a homogeneous solution, first drop the same as the last. Why? Like this summer or last year, because of something called, I like to call famous boyfriend, famous girlfriend. Now what does that mean? If I have a famous girlfriend or boyfriend, let's just say, and I don't know, Selena Gomez?
Selena Gomez.
Is she dating someone famous, or she was?
Yeah, the weekend.
I don't know. Let's say she was dating Justin Bieber. Bible? Is it? Okay, so let's just say it's 2 people that you really know, think is cool, you read in Paper Magazine. Let's say you're all in the gymnasium, like 1,000 people, no teachers, I'm going to say no t-shirts, that's kind of weird, but no teachers, okay, to supervise anything, and they come hand in hand walking. So let's say they go hand in hand, they're walking, okay? Not sure why.
It's an arrow.
Okay. She might be taller. Who knows? Not sure why they're walking, or why her torso is separated from the leg. Not necessarily why they're walking with their hands up. It's kind of weird. Okay. But they're walking hand in hand into the gymnasium. Now they're really famous. They're good looking, I guess. People like them. They're attracted to them. So what you can expect to any famous, good looking couple, if there still are, and I'm just making this up. Okay, I haven't read my People magazine yet. Anyway, the point is, if a famous couple comes walking to a gym, what's going to happen?
All the guys go.
Oh yeah, right. All the guys are going to surround the girl. So here's the girl. Okay, so all the boys, all right, would surround the girl, and then all the girls would surround the what? Generally speaking, okay. And they would get what? Pulled apart. Can you imagine that? That's how water reacts. Waters are going to basically surround each ion and pull them apart. Now why? Well, one of the ions is going to be positive. One of the ions is going to be negative. That's why they stick together. This is +2. This is -1. You need 2 of them. So what does that mean? The +2 attracts a negative. They stick together. But now water, as you learned, has a negative end and a positive end. Again, that's a polar molecule. So what happens to the positive ion, obviously, is the negative part of the water molecule is attracted and surrounds. More importantly, it competes for the charge. Let's do this slowly. Again, it's fundamental that you can visualize what's happening. So if I have zinc, he's +2. And let's say I have the nitrate, he's -1. They stick together in a crystal. If a solid is in a crystal, it sticks together, all right? And it goes in all dimensions. That's what a solid is. But water can get in the crystal. And where's my crystal? Okay? Where did I put my crystal? Ah, there you are. No? Okay. Here's my crystal. Okay, and this could be a crystal of zinc nitrate. Now, all crystals can be a little bit different, but they make a regular geometric pattern. Very stable, low entropy, low energy, right? Water can get in there. The negative part of water can get in this crystal on the edge and do what? Do a famous boyfriend, famous girlfriend to it. And what happened is zinc no longer feels the nitrate, and that's how they get pulled away. So water can dissolve solids because it competes for the charges in the crystal. Only if these attractions for each other are weak, right? Now, how do I know they're weak? Coulomb's law, my gosh. Is zinc nitrate soluble? Yes, it is, because I wrote aqueous. How else do I know that? Well, party people, back to table F. I affectionately call table foo-foo. All right. Why? Because I'm tall. Where are we? Oh, I was at the same place. Okay, my bad. So let's go back to table F. And we'll table F around. And there we go. It's table E and then table F. You should have this. I gave this to you. Oh, Christmas. All right. Moving slow here. I can do this. All right. Now, this is a solubility table. It tells us if something does dissolve. Now, you had this last year if you took reagents. If something's soluble, that means the salt, the crystal compound that's made up, if it has one of these types of ions in it, in presence of water, will dissolve and make an aqueous solution. Notice the charge. Hey, notice the size of the charge. What does that mean? If I have an ion that's +1 or -1, the coulombic attraction between the positive and negative in the crystal is what?
Low.
Right, and water can compete with that and pull them apart. Look at the ones that are insoluble. Oh. Now there is an exception. There's reasons for that. Hydroxide's a really small ion. Okay? Sulfate has some other things going on, but generally speaking, if you've got high charges, what does that mean? Because you're what? Coulomb's law, force of attraction equals the size of the charge over the distance squared, right? So the charge is higher, the force between these is greater, water can't break apart. Got me? That's important. Okay? Now, back to reality. Up there goes gravity. Now, here's the key here. When I write zinc nitrate, I'm going to say all year it's a Kardashian wedding. No. We write it together in Regents chemistry, but that's not a really good interpretation for us. They're not really together. If it's aqueous, isn't it dissolved? Didn't the water get in and pull apart? So what you really have is zinc +2. Now, of course, water, the negative part's around it, but we're not going to draw that. And of course, we have what? NO3- ions. On this side, what do we have? Of course, copper +2. We know the O end of the water is surrounding them. And of course, the nitrate ion, what's surrounding them? The H part of water, correct. We're going to leave that out. But these ions are free to move, and that they're homogeneous. So, what they do, party people, is since this reaction was written like this, zinc solid plus copper nitrate went to zinc nitrate. This is the full reaction. And he made copper. Notice something. Zinc went to what? What's the charge in zinc nitrate? Zinc plus, right. Zinc solid, oops, it's getting smaller, goes to zinc +2. The copper +2 in solution pulls the what? The electrons out of it, and it becomes what? Anytime you see a metal stand alone, it's a 0. What's its phase? Solid, just like we did yesterday. That's the reaction, but they don't write that. They don't like that because why write that way if it's really not together? So, who's just hanging out here? Who's not really part of the reaction? The NO3 ion is not really part of the reaction. So what they do, party people, is they get rid of the spectator ion. It's not part of the reaction. Isn't really zinc becoming zinc plus 2? Isn't copper plus 2 becoming pure copper? So they get rid of, I'll just do it over. They get rid of the nitrate ion and say, okay, zinc plus the copper plus 2 goes to what? Zinc plus 2. Because that's what's really happening. These guys are just hanging out. And we use nitrates to deliver the ions. Why? Nitrates are always what? Which means if you have a nitrate with the ion you want, it'll dissolve. Think with me for a second. Why? Why does nitrates, all nitrates, no exceptions, if they're part of a crystal, dissolve? I have 4 atoms. Here's a nitrate. Looks something like this.
Neutral.
Actually, the nitrate ion is -1. I'm spreading that -1 where? Over 4 atoms. Coulomb's law. What's the diameter of 4 atoms?
Large.
Large. So therefore, the attractive forces in nitrates are going to be weak. That's why they're soluble. Okay? So that's the real reason. Now, the question is, even though we like to, just like homework, not to write the spectator ion, I need you to understand that nitrates could be doing something here. What does the salt bridge do? Right now I have no voltage because this beaker got negative, or did it get positive? It's becoming what? It got positive. And this beaker is losing its +2, so it's getting electrons won't flow. So we've got to keep these beakers from changing their charges, maintain electrical neutrality. I put in a salt bridge. Okay? Now, I got my voltage, which we now know equals a what? What is a voltage? It's potential difference of charge, but it's an voltage is equal to the energy per coulomb. It's the energy that pushes the charge. It's where we get the energy from. We're creating, listen, I've got zinc. Does zinc have electrons to give? Can it? That's important. I've got copper +2. Does it have ability to pull and attract electrons? Reduce? Absolutely. Put them together. You created a scenario where we have all this built up of what? Electrons, and zinc can now push and copper can pull to, and that creates the energy for charge to be pulled. So this has a high potential difference. Don't forget that. Now, electrons flow from what to what? Always the one that produces them. Now, I didn't do this nice and neatly, but I will right now. These are the half reactions. Some people are weak on half reactions. I'm going to pull out what changes. Zinc, 0, which we know is the solid, becomes zinc +2. Why am I separating this entire reaction? Because I want to see who is doing what. These are called half reactions. First law of half reactions, pull out on one side, I had zinc on the reactant side, still here, pull out what it changes to, okay? We'll keep this simple, we'll go back to the college balancing in a little while. In fact, if we do the college balancing, we'd say, balance everything other than the O's and the H. 1 zinc, 1 zinc. I'm good. Are there any O's? No. If there were, I would add water, remember that? And if I had the extra H's, I'd add H pluses. But I don't have that, so this is easy. Now I have to balance the charge. And this is the rule. Both sides of a half reaction have to have the same charge. Since redox is about electrons being gained or lost, here's my check. I got to put the electrons. What's the difference here? Really, it's 2 electrons, right? By mistake, if I do this, here's my check. -2 and a 0 is what? And this side is +2. I made a mistake. Okay? So I put the 2 electrons here. That way, both sides are balanced. We balance the reactions, we balance the mass, and we balance the charge always. Cool, I got one of the half reactions. Why is it half? Because in redox, you have reduction, gaining, and oxidation. There's a transfer of electrons. So, next one. Copper +2 was written here. It goes to copper 0. Is there any oxygens? No. No waters to add, no H pluses to balance. There's a difference of how many electrons? 2. I got to put them so that both sides of a half reaction are equal. Do not fall in love with the idea you put them so that both sides equal 0. Both sides have to be, okay, the same charge. In this case, I'd have to put 2 electrons here. And if you're writing half reactions, you should understand intuitively, electrons have to be on opposite sides. Someone is producing them, someone is gaining them. I'm adding the electron here, okay, and you should be able at this point to recognize that gaining electrons is what? GR. Reduction. Hey, the reduction potential chart you have all looks like this. And if electrons are on the product side, you're producing them. This, of course, is oxidation. This, of course, is reduction half reaction. Now, something else you need to do overall we'll get to. You should balance your electrons at the end, but I don't care about that right now. Okay? Now, net potential. Yesterday, how do I get net potential? This is how you should be doing your business here. Write your half reactions and find the net potentials. So I go to my reference table, okay, and let's go here, just like we did yesterday, and you're going to do this a million times. This is the quantitative way. We find, I always go to find the ones reducing. We found that copper +2 was reducing. So as written, I changed nothing. As written, this is a reduction chart. They found these values as reduction by convention. That's what they chose. The value as written, find the reduction as written, 0.34. The only one now is oxidation is the reverse of this reduction. And as we learned yesterday, if you're really good at getting reduced because of how you're made, Coulomb's law, all of the things in between, if you're good at gaining electrons, you can't be good at losing them. If metals are big and don't attract their electrons, how could they ever be good at gaining them? They're not. If I'm really small, Coulomb's law, have a lot of protons from my size, if I'm good at attracting them, how can I be good at losing them? I can't. Okay? There's no ambidextrity in chemistry. Okay? So to get oxidation, you have to do the reverse. And we flip the sign. It's a thermodynamic quantity we'll get to and define it later, but we flip the sign. For those that had Regents chemistry, remember delta H was positive one way, it becomes negative the other. We'll get to those things. But, so now I find who got reduced. Zinc. That one I have to flip. The oxidation I flip. So zinc goes this way. And that I flip the sign. Positive 0.76. Add them together, and that's where I get my 1.10 volts. That's how you should do your business, okay? Always keep reduction, okay? But you should understand, they're going to give you a chart on a Regents, or sorry, on an AP test. They always give it as reduction potentials. The one it oxidizes, you have to flip. Okay. Now, this is based upon standard conditions. We can manipulate that, and we did so with the homework. Now, before we do that, let me speak to them. I'm going to get rid of this now, but that's how you should figure this out. All right? So let's get rid of this part. Now, I want to talk about this spectator ion. Now I have this tube here. And let's just make it a shortcut. This is my salt bridge, just like your dialysis tubing a couple of days ago was. And we're going to make the batteries again. All right. Now, let's say I have sodium chloride in my salt bridge. That's my salt. Is it soluble? What's the charge of anything in this row? It has 1 valence electron, so it likes to what? Lose it, so it's +1. If you don't know, you can go to your reference table that I will give, and you'll see sodium is +1. This guy is 1 away from gaining to become stable. Remember that stuff? So all of these guys are -1. If you're uncomfortable with that, I'll give you the reference table that you can look up. That's not a big deal. Eventually, as you do this, you'll be like, that's simple, I got it. No need to look it up anymore. Right now, I could care less. So when I write the formula, NaCl, that's what it is. Now the question is, this has got to be free ions for this to work, so is this soluble? Yeah, how do I know it's soluble? What's the charge of sodium? What's the charge of chlorine? The charge is high, so it's soluble. There's your solubility rules. 95% of your solubility rules. By the way, they make you memorize in college. You don't have to if you understand what this means. There are some exceptions you do have to. And their exceptions are really cool to know why they're exceptions. There's a reason for it. There's things going on. but 95% of your solubility rules is that. So this really means what? Remember, if I write it this way, what does this really mean? If I put aqueous, what does it mean? The ions are interacting with the water, pulled apart, and I have Na plus and Cl negative. Okay, good stuff. Now, of course, I'm producing zinc plus 2. I got to keep this beaker from getting positive. What? The chloride ion comes down. Yeah? You with me? Cool beans if beans are chill. Where does the sodium go? Down this way. Okay, good beans too. Because it's going to replace the positive that's lost. Am I done here? Is that it? End of story? Well, wait a minute. What do I need on this side of the beaker to balance off? What if I start running out of sodiums? What if I ran out of sodiums? Wait a minute. Couldn't the zinc plus that's made go that way? Why would the zinc plus 2 go that way? Right. What else could happen? What do we need in this beaker? It's getting positive as I make zinc plus 2, right? Couldn't the nitrate move up this way? Who doesn't understand that? What also can happen?
Wait, so if you run out of salt...
I'm just saying that the ions flowing in the salt bridge maintain electric travel. We're not stuck by the ions here. What else could happen? If I have a lot of... Couldn't the copper be pulled through? Would the copper be pulled through? Would the copper go? If this is trying to be what? It's trying to be positive, right? So this is becoming positive over time, right? Zinc is becoming positive. Positive 2, that's the half reaction. So you wouldn't expect the copper to flow, right? But you should be able to understand why they all flow there. Okay. Now, is the 1.1 I got, obviously you can see the answer there, the 1.10 I got, that's it. That's what it is and that's it, right? There's no changing that. Is that true? Right. I can manipulate the heck out of that. That's what chemists do. We figure out the limitations based upon the pathway in nature, and then we manipulate the heck out of a reaction to make it work if it can. If there's no possibility, chemists can't make any reaction go. The first alchemists are trying to make everything into gold. Well, there really isn't any pathway on a macro scale to do that. You can do it on a micro scale by bombarding protons to mercury and for microseconds, but we can't do anything we want to do. But we can maximize like some reactions don't work very fast. They're just very slow. We've figured out how to increase the spontaneity, even though rate and spontaneity are different. So I need to step back here. Manipulation of this is based on something called equilibrium. I want to explain this today. Okay, and that was part of your homework. Okay, you got this question is, what can you do to the concentrations here? Okay, and so if you noticed, I have a greater than expected voltage. We talked about this. Now, why do you think? Well, one of the reasons is I'm at 1.1 if I have a certain concentration of copper ions. Well, my concentration is greater than those conditions. So if I have more copper than those conditions, don't I have more copper plus 2, I should say, okay, pulling the electrons through? And isn't that more of a pull going to make more of a force? Yeah, we can manipulate it. We're going to mess with this lab, but I'm going to design a new lab for you this year. Okay, the next lab that we do, where you guys are going to design a battery on your own, and the race or the test is going to be who can build the battery with the greatest voltage based on the things I give you. You can't go out and get some exotic things. I'll give you some list of supplies, and you got to figure out who can produce the greatest voltage. Okay? Now, to understand that, we have to understand spontaneity more. So by adding more copper plus 2, look at me, party people, I'm making this pathway forward bigger. And that's what spontaneity is. It's a pathway. and we are allowing that pathway to go forward. Last year you learned about Le Chatelier's principle, where you're talking about add a stress to a reaction, and the reaction does what? Undoes that stress. And that's a nice little way of explaining it, but Le Chatelier's principle is, if we add a stress to a reaction, I could force it to go one way or the other better. What does that really mean? I'm making one of the directions, what? More favorable, more spontaneous. Okay? So I'm going to stop here for a second, and I have to go back to the written things. And guys, I really believe that you need to read snippets of my book here that I do post. Okay? Right now it's all under that one Coulomb's law, but now I posted some here. So let's take a step back to understand how we do this. Really important stuff here. Okay? Connection, spontaneity. Let's look at something entirely different than a battery, a chemical reaction. And these are two NO2 molecules in equilibrium with N2O4. That is happening in something called an ampule. This is not a brown colored, or whatever color you think this is, because I'm not good with colors, tube. What it is a sealed, clear tube with a brown gas in it. Okay? Now, NO2 is a brownish red gas. N2O4 is clear. These guys are in equilibrium. Now, what does that mean? That means for every two of these, you produce one of these, but double arrow means, if you're at equilibrium, as fast as NO2 comes together to make N2O4, N2O4 decomposes. I'll say that again. As fast as two NO2s collide and synthesize N2O4, one N2O4 decomposes. Now, to look at that change, let me give you this scenario. All right? So if I have a graph of, this bracket represents concentration. Moles per liter is molarity. This is how much of the NO2 I have in my ampule. Let's say I start with 100% N2O4. 100%. Am I at equilibrium? No. What's going to happen is some of it's going to what? React to make N2O5. So I'm going to make some. So some of this is going to go forward. There's a pathway for it to come together. So some of it comes together to N2O4 and it just makes some. Over time, though, what happens? Why does the concentration of these two gases level out? I've reached equilibrium. The rate of making N2O4 is equal to the loss of NO2. That's equilibrium. It's boring. Anything happening? Things are changing places, right? If I have 10 people on this line, 2 people on this line, I make each person change lines, 1 person a minute. Are the number of people on each line going to change? No. Are the people? But is any work being done? No. There is zero spontaneity here. There is zero direction. Nothing is going on. Yes, there is movement of molecules back and forth, but there's no work being done. There's no real direction because none of these are changing. Was there direction here? Where is the greatest amount of pathway? Here or here? A or B? A! There was a great change happening. And then the what? The slope, for those like the math, starts what? Bottoming out. The slope is the steepest here. Look at this. This had the greatest rate of change. Clearly, in the beginning, there was a pathway. Why would there be a pathway? Okay? Because the universe allows for N2O4. Now, listen to me, bro. How come they don't, did I just say listen to me, bro? I sound like my son, all right? Keep telling him, I'm not your bro, okay? Too much YouTube, all right? N2O4 does not equal that. They don't equal. Who's favored at this equilibrium? When they reach equilibrium, the rate of making NO2, N2O4 get there, who's favored? Who is still favored? Right. Can anybody tell me why, you think? Yes. Even though we start out all of this, we do make some, eventually it evens out here. Once they even out, why do you think NO2 is favored? You first.
Because N2O4 splits into 2 NO2.
Ooh, you're really close. What do you got?
I was going to say 2 NO2 maybe.
What about the fact that spontaneity is tied to entropy, dispersion of energy? one of these, they're locked together. Two, they're more freer. Isn't it going to be a scenario where there's going to be a more of a what? Favorable direction to make NO2? Because they're freer. Don't forget, spontaneity is a pathway based on dispersion of energy. What does a battery do? They got all these electrons the metal has. They can be easily distributed if someone pulls on them really good. That creates the force. All right? So, in this beaker at room temperature, I've got what? A mixture of NO2 and N2O4. This is clear, this is brown. Hard to see, but you clearly see what? There's more brown than clear, hard to understand that, but that's what's happening here. Now, this is the money shot here. Okay? The universe's entropy must always increase. You probably heard that. What does that mean? Energy gets dispersed. In a battery, it's potential energy to low. When's the battery dead? When the voltage goes 0, which is when we're at, right, at equilibrium. There's no work being done. There's no pathway. There's no direction. So we've got to stack the cards in the favor. Heat flows from what? High to low, because heat has tremendous amount of energy in an area. It's going to disperse out eventually so that the heat makes the surrounding temperatures eventually the what? The same. Think with this for me. Me and my friends, I heard of some people going to Central Park, and they would sit in Central Park, and we would measure the blades of grass growing in they would measure the blades of grass growing in a day, and they'd mark it down. And when we're doing this, it's a long day, it's a lot of, here it's a lot of fun. In any case, when they were measuring for a full day, you're not moving much because you don't want the blades to move as you have I've heard you have your own little tiny square. We're huddled around. They're huddled around out here. Okay. In any case, as we're measuring blades of grass growing in a day, as they are, as I hear, darn it, keep this making me. It's not about me. Okay. They're not moving very fast. So we got 10 people of the people I think could be my friends, okay, measuring blades of grass in a 1 square meter plot of Central Park. And gosh darn it, someone playing frisbee runs into them, okay, and knocks us over. They go tumbling, okay. Are the slower moving objects who have less energy going to spread their lower energy and move to faster mover objects, or faster moving objects who have energy going to get to the slower moving objects? Right, he goes from hot to cold because of this. Battery works because of this. We're going to distribute that potential energy, okay, in the system. All right? This works because I'm going to favor more NO2s at equilibrium. But at equilibrium, though, nothing is occurring. We're 0. Now, this is really important. This is the crux of everything. This is the crux of everything. Okay? This, by far, is my most important chart. Okay? Here's my equilibrium. Rate of the forward equals rate of the reverse. When I started with 100% NO2, I had the greatest spontaneity. The rate of the forward was at its fastest because there was no what? There was no reverse. Why? Because there was no N2O4, right? So the rate of the forward was tremendous compared to the reverse. Therefore, the greatest direction occurred in the beginning. But as I start building up N2O4 and the percentage of NO2 drops and NO2 increases, okay, isn't there a reverse reaction? And if there's a reverse reaction occurring, and if there's a competing pathway, big arrow, small arrow, and they start becoming what here? The same. So as I go forward, my level of spontaneity drops because there's a competing pathway. Does that make sense? So the farther I am away from equilibrium, the more spontaneous. This is reaction death. No more work gets done. The forward equals the reverse. The forward spontaneity is what? Equal to the reverse. When a battery is at its maximum voltage, it's so far away from its equilibrium. Okay? Does that make sense? There's competing pathways. Here there is no reverse pathway. If you're really good at oxidizing, you're terrible at what? That's the same idea here. There's no reverse pathway that could happen, so therefore this is the most spontaneous point. So what do we do as chemists if I want to make N2O4? You know what I do as a chemist? I keep taking the product out as it's made. Think with me for a second. If I keep taking the product out as it's made, the reaction stays at this point is the most spontaneous. That's what we do. We mess around with stuff as chemists. We take stuff out as it's being made. And so the reaction thinks it's still here, and the reaction keeps going until I run out of stuff. If I put it in an ampule, nothing happens. Okay? We can mess around. And this is Le Chatelier's principle. Le Chatelier's principle states, if you've got a reaction that's dead at equilibrium, if you do something, the reaction will do the reverse to try to regain that balance. I don't call it a balance, I call it death. Everything works toward zero entropy, zero work. Unfortunately, the universe is ticking. The universe is going to die at some point. Not in our lifetime, not even close. Why? Energy is going from small points, stars, and dispersing out. What happens when all that energy eventually disperses out? We're all at the same temperature. And when we're all at the same temperature, there can't be any more chemical reactions. Okay? Take a break.
Wait, Mr. Rodsky.
Yes.
I want to say something.
It's off.
What's that?